So this is a question from Chemical Engineering GATE 2015, question number 59. An isothermal steady state mixed flow reactor or CSCR of 1 meter cube volume is used to carry out the first order liquid phase reaction A gives product. Fresh feed at volumetric flow rate of Q containing reactant A at concentration Ca0 mixes with the recycled stream at a volumetric flow rate of Rq as shown in the figure below. It is observed that when the recycle ratio R is equal to 0.5, the exit conversion XAF is equal to 50%. When the recycle ratio is increased to R is equal to 2, then the new exit conversion in percent will be option A 50%, option B 54.3, option C 58.7 and option D 63.2. So this is a question from recycle reactors from chemical reaction engineering, and the reference NPTEL series can be found in module 1 lecture 26 reactor design for MFR and combination of reactors, chemical reaction engineering 1, homogeneous reactors by Professor K. Department of Chemical Engineering, IIT Madras. So here they have given us a CSTR with recycle. So as you can see in this picture, we have an initial flow rate of 0.5 meter cube per minute and initial concentration of 1 mole per meter cube, and this enters a CSTR and the final concentration will be CAF with the final conversion as XAF. And the recycle stream is also given as RQ. That means the recycle ratio is basically R. And they have said that when the recycle ratio R is equal to 0.5, the exit conversion is 50%. That means this XAF will become 50% for R is equal to 0.5. Then when R will be increased to 2, what will be the exit conversion? That is what they have asked us to find. So let us see how we can proceed for this. So let us take two cases. So case 1, CSTR with no recycle. Okay. So let us take a CSTR like this. Now Ca0 as our initial concentration, Q will be our flow rate, and let's say tau is our space-time with V as our volume, and CAF will be our final concentration. Okay. So let us take the reaction as A gives B just to keep things simple, and it is a first order reaction and the reaction rate is equal to KCA. So for this, if we write the design equation, it will be tau is equal to V by Q, and that will be equal to Ca0 minus CA F by KCAF. You can also write this as Ca0 into XAF by KCAF. Okay. Now we can write the CAF as Ca0 into 1 minus XAF. Right. So just rewrite this equation for tau. Tau will be Ca0 XAF by K into Ca0 into 1 minus XAF. So Ca0 get cancelled. If we take this K from the right hand side to the left hand side, it will be tau K is equal to XAF by 1 minus XAF. And if we rearrange this a bit more, we can get XAF is equal to tau K by 1 plus tau K. So this is the final conversion without recycle. Okay. Now let us take the next case, case 2, as CSTR with recycle. So we'll draw simple schematic here. So we have a CSTR like this. This is our inlet concentration Ca0. This is our outlet CAF, and let this be our recycle stream. Now the recycle ratio will be R, and this flow rate here will be R into Q. So Q is the flow rate initially, and again we'll take tau and V as our space-time and volume of our reactor. Right? The flow rate here also will be Q. So one more thing we need to know, that the concentration at the inlet now has changed because of this recycle. So the concentration at the inlet of the CSTR will be Ca1, and the flow rate at the inlet of the CSTR will be Q1. So we have two new terms here, Ca1 and Q1. So let us see how we can find these two new terms with respect to the known values. So the design equation basically says tau is equal to V by Q1. Now this is not V by Q, this is V by Q1, and that will be equal to Ca1 minus Caf by KCAF. Notice the difference here. So in the previous case with no recycle, the design equation was tau is equal to Ca0 minus Caf by KCAF. Here, because of this recycle, the concentration and the flow rate at the inlet has changed, and now the design equation for this CSTR will become V by Q1, which is equal to tau, that is equal to Ca1 minus Caf by KCAF. Right. Now let us take a flow rate balance throughout the system or at the entry point. So basically this part. So this was Q, this was RQ, and this became Q1. So we are talking about this entry point. So if we write the balance, Q1 will be equal to Q plus RQ, right? Or basically Q1 is equal to Q into R plus 1. So out of these two unknowns, now we found out Q1 in terms of our initial flow rate Q. Now we need to find Ca1. So for Ca1, what we'll do is we'll write the component balance of A at entry point. So here it was Ca0, here it was Caf, and here it is Ca1. So if we write the component balance, Ca0 into Q plus CAF into RQ is equal to CA1 into Q1. So basically this is just in minus out is equal to 0 kind of balance. So if we rearrange this a bit, we can write CA0Q plus CAF RQ will be equal to CA1, and we just found out the value for Q1. Q1 is Q into R plus 1. So just substitute it there. It will be Q into R plus 1. So from this equation, this Q will get cancelled from all these terms, and final will become CA0 plus CAF is equal to CA1 into R plus 1. Now from this we can write CA1 as CA0 into, sorry, there is an R here. Yeah. So the equation will become CA0 plus CAF into R is equal to CA1 into R plus 1. Now we can write CA1 as CA0 plus R CAF by R plus 1. Okay. So now we have the concentration CA1 and the flow rate Q1 at the entry point. Right. So we'll come back again to the design equation. Design equation of CSTR with recycle. So that design equation was basically tau is equal to V by Q1 is equal to CA1 minus CAF by K CAF. Right. Now what we'll do is substitute Q1 and CA1 in the design equation. Okay, so V by Q1 is basically Q into R plus 1, and that will become CA1, and CA1 we just found out here, that will be CA0 plus RCAF by R plus 1 minus CAF the whole by KCAF. Let us try to simplify this. So V by Q into R plus 1 is equal to, if you take the LCM and do some rearrangement, it will be CA0 plus RCAF minus RCAF minus CAF the whole by R plus 1 into KCAF. Now this RCAF and RCAF will get cancelled. This R plus 1 on the right hand side and R plus 1 on the left hand side will also get cancelled, and we'll get a final equation V by Q is equal to CA0 minus CAF by KCAF, and this is equal to tau. So this is the tau for CSTR with recycle. Now if we look carefully, the tau for CSTR with recycle is basically equal to the tau for CSTR without recycle. Right? So basically what this means is, if we try to find the conversion here, so for CSTR with recycle, tau is equal to CA0 minus CAF by KCAF, and that is CA0 into XAF by K into CA0 into 1 minus XAF. CA0 get cancelled. Tau K will be XAF by 1 minus XAF, and XAF will be tau K by 1 plus tau K. So this is same, the conversion for CSTR with recycled is same as the conversion of CSTR without recycle. Right? So basically what this means is recycle has no effect on the conversion of CSTR. So this is the important takeaway from this whole numerical manipulation that we did. So what this basically means is whether R is equal to 0.5 or R is equal to 2, whether the recycle ratio is 0.5 or it is 2, the conversion remains unaffected. That means the conversion will remain at 50%. So no matter how much the recycle ratio is manipulated for a CSTR with recycle, the conversion will remain the same as the conversion from a no recycle CSTR. Right? So here the right option here is option A, 50%.